Thank you so much. Yeah, thank you so much for everyone being here and so forth. Today I'm going to give a talk called An Introduction to Mathematical Modeling in PINNs. And the sort of shorthand for it, we can just say is modeling with PINNs, right? So it would be remiss of me to not also give some brief acknowledgments, because really this work is a collaborative effort between a lot of different people. So I just want to give some brief acknowledgments. Firstly, mainly to Dr. Liang Kong, who's pictured here. He's my research supervisor as well as paper co-author. Really, without him, none of this would have been possible. Secondly, to Dr. Nguyen, for his dedication to teaching differential equations, his infinite understanding. I first took differential equations here at UIS with Dr. Nguyen. Nextly, to Professor Lee. Thank you for accepting me to present here, hosting, organizing, making this reality. Dr. Shan, of course, when I first applied to UIS, he was my first point of contact, introduced me to really the entire math department. So without him, this would not have been possible either. And lastly, you guys, thank you so much for attending, giving me a little part of your Friday so I can talk to you guys about PINNs. So with that, let's get started with modeling with PINNs. So if there's anything you should take away from today's talk, it's going to be these three big ideas. The first big idea is that physics and machine learning have certain drawbacks when it comes to modeling, right? So physics and machine learning have some drawbacks. The second big idea is that PINNs is a combination of that physics and that machine learning. PINNs is that combination. And the last big idea is that PINNs is going to improve upon these drawbacks, okay? So not only is PINNs a novel combination of the two, it actually improves upon those drawbacks. I'll get into the details of this a little later in the talk, but for now, just sort of remember these two things. There's certain problems, there's drawbacks with traditional modeling. PINNs is a new approach to modeling, and then PINNs actually improved upon that modeling effort. Okay, so these are the three big ideas. Are we building into this by first talking about modeling in abstract? Oop, not sure why I jumped there. Uh, talk about modeling in abstract, followed by the different approaches to modeling, then talking about PINNs more in depth, then finally get into PINNs and how it relates to our research, and then end with conclusions and so forth. So with that, let's get started with modeling. So modeling is the act of representing our world in a way that's sort of useful to us, right? Typically, we do this through mathematics. So I want to sort of motivate the question of why we want to care about modeling by first talking about its importance to society. So really, modeling helps us test a bunch of hypotheses we might have about the world and to find these solutions at a very low cost. Likewise, the results from these models help us make sort of really big executive decisions that we can then implement in different ways: risk assessment, policy formation, metric optimization. And this exists across all sectors, right? So physics, biology, economics, law, etc. This is a very applicable thing that happens for like the entire span of our livelihoods. So at this point, I want to get into a specific model or a specific example of what we might want to model, right? So imagine in this case, we have a picture of an apple that's about to fall from a tree. And maybe some questions we might want to ask about this apple is how it falls, right? Does the apple fall straight down? Does it tumble? Does it roll midair and so forth? This is sort of a toy example of a natural phenomenon in our world that we want to model. Now, when we think about trying to model this apple, there's these sort of three main questions we need to be thinking about, these guiding guiding principles. The first one is the trade-off between complexity and interpretability. So a highly complex model is a model that's able to account for all the tiny details in a system. So maybe in our apple example here, it's going to be something that accounts for the humidity of the air or the wind speed or something like that. Highly complex models, because they sort of capture everything, tend to give us much stronger results. But that always comes at the cost of interpretability. Highly complex models are have low interpretability. Low interpretability, they're certainly harder to use, and of course, also harder to sort of demonstrate or talk about your results to a wider audience. A second trade-off is going to be between specificity and generalizability. So a highly specific model is a model that's just optimized for one specific problem. And as a result, we expect to see better performance. But when you have something very highly specific, it sort of also obviously suffers from generalizability. We can't apply that model to many other different things. And thus, we might need to make different models that comes at different costs. And lastly, the trade-off is going to be between performance and cost. So a highly performant model is one that's robust, it's powerful, it's accurate, and so forth, but that will also cost more money, right? It costs more time, more training data, more compute, and so forth. So these are the three sort of guiding principles we need to think about when we try to model something such as that apple example. Now, there's a lot of different things that we may want to model, and different things in society may want to prioritize different sides of those trade-offs, right? Which is why we have different approaches to modeling. One such approach is the physics approach. And as the name suggests, a physics approach is going to use physics laws, right? Typically math equations or differential equations to be able to approximate that phenomenon. So this then begs the question, okay, what are differential equations? Well, differential equations are equations that have derivatives of one or more unknown functions with respect to one or more independent variables. And we'll get into this. This will become more clear with examples. So down here we have two differential equations. The first one is a differential equation. It's called an ODE, ordinary differential equation. And we know these are differential equations because we see the derivatives here, dx, dt, etc. And in this case, it's an ODE because it only has one independent variable, which is the t here, ordinary differential equation. And the second one here is a PDE, partial differential equation. And these are PDEs because they have two or more, so x and y, two different variables, right? So this is about the extent of which we know about differential equations for this talk. But differential equations play a really big role in PINNs. So now let's think about what a physics approach might look like to modeling applied, right? So when we think about our apple example, and remember, we want to know how the apple falls, we can think about sort of citing a relevant physics law. So in this case, maybe Newton's equation for gravity might work. So we take Newton's equation of gravity, take the variables, plug them in, compute it, and we get a result, in this case, acceleration. And the sign of the acceleration, whether it's positive or negative, tells us the direction in which the apple falls. Does it fall down or up? And this sort of gives us a very rudimentary physics approach towards modeling this falling apple. Now, just to sort of sum up everything for the physics approach, the main important features that we want to know about a physics approach is that physics approaches tend to be built from first principles in physics in mathematics, right? So in this case, this equation of gravity is a first principles in terms of physics and mathematics. And likewise, we tend to use a lot of analytical solutions. These are sort of clean solutions that come out to exact answers. They're not really approximations. So these are sort of the two bounding features of a physics approach to modeling. Now, moving on to some real world examples, because we don't want to just stay with the apple. Here is an example of a physics law or a math equation for harmonic oscillation. So harmonic oscillation tells us the movement of a spring, maybe how bouncy it is, something like this. Another example is the Burgess equation, another physics law. It's also, again, it's a differential equation. It's just math. And the Burgess equation will tell us the behavior of a nonlinear wave in a fluid flow system. That's just fancy speak for imagine it like a honey. If you dip your finger in honey, how does that mold in that system, right? That's sort of what the Burgess equation tells us. And when we think about the physics approach to modeling, we always have to think about those guiding questions, right? The trade-offs. And it happens so that the physics approach tends to prioritize things on the right-hand side of these trade-offs. Physics approaches tend to be more interpretable, right? When we think back to that equation for gravity, Newton's equation for gravity, it's interpretable because we know what those variables mean. We know where we got them. We know how to manipulate them mathematically. So it's very easy to use. Likewise, physics approaches tend to be much more generalizable, right? So the equation for gravity, we can apply it to many things, not just the apple, and certainly not just things on our planet. It can be on other celestial bodies. And lastly, the training costs, right? A physics approach is very cheap when we think about comparing it to other kinds of approaches. So if we didn't have the pen and paper, we didn't have the equation that we could use, we'd have to go out, find an apple tree, wait for it to fall, capture it in video, et cetera, right? So this is certainly much more costly than just staying indoors and being able to find that sort of simplistic model on paper. Now, this sort of brings us to that first big idea of today's talk, right? Which is that physics and machine learning, but so far we've just talked about physics has drawbacks. And these drawbacks are that the physics approach, by prioritizing this side, the right-hand side, it loses out on advantages from the left-hand side, right? These are the drawbacks the physics approach has. And now let's say we don't really care about the things on the right-hand side, and maybe we want the things on the other hand of this trade-off. And that's where a machine learning approach comes in. As the name suggests, a machine learning approach uses machine learning algorithms to be able to approximate such phenomenon. This sort of begs the question, well, what is machine learning? So just sort of a high-level overview, machine learning is a subfield of AI, artificial intelligence, that develops algorithms, develop code that can learn from raw data, learn. And learn is the really key part here, at least for this part of the talk. The difference between a machine learning code and sort of normal software code is that with normal code, you have to give explicit instructions for it to do something, while the machine learning model can learn on its own. So for example, if you want to solve some sort of question or problem with normal code, you need to know the answer or at least know how to get the answer already. So you need to know exactly the process and then give that exact instructions to the code, and the code will very deterministically do the thing you tell it to do. However, with a machine learning model, it's a little different. You don't really know what the answer to this question is. So you're going to have a machine learning model come in and learn from its data, learn from its code, and so forth, and it'll come to arrive at some sort of answer that is useful to us. I'll go into this a little bit in detail a little bit later. But this is just sort of the difference, high level wise, between machine learning and normal code. It's the learning feature, the ability to learn. So now let's think about what a machine learning approach might look like for our modeling in the case of the apple, right? So let's imagine instead of the equation for gravity, we now have 1 million pictures of falling apples, okay? These tons of pictures of apples, and we're going to feed them into this blue brain, this machine learning model here. And what a machine learning model is going to do is it's going to look at all these millions of pictures of apples and extract some sort of pattern, learn some sort of pattern about how that apple might fall. Then it's going to, based on this pattern that it's learned, it's going to come up with a prediction. So based on all these pictures, I think the apple is going to fall this way, right? Something like that. Now, particular to our talk, we're really only concerned with one type of machine learning model, and that's going to be the neural networks. So neural networks, they use interconnected nodes and a loss function to make predictions from data. So it'll make a little more sense when we get into the schematics here. So down here is a picture of a neural network. And we can think of a neural network as a really big math function, right? So here in the yellow, this is our input, our independent variables, our plugins, et cetera. We're going to plug these inputs in to our neural network function. And then it's going to pass into the green section here. The green section represents the computation part of the function, right? So the operations, the plus, the minus, et cetera, the things that edit the output. And the red here is going to be the answer that you get, the output, the dependent variable, and so forth. Now, I mentioned this a little bit before. Machine learning models are able to learn from their mistakes. Neural networks are especially good at learning from their mistakes. And what do I mean by that? So remember here in terms of our machine learning model, remember that the machine learning model makes some sort of prediction. And let's just say for this example, it predicts that the apple is going to fall upwards, right? This is a neural network. And what it does is, once it has its prediction of the apple falling upwards, it's going to compare it. It's going to compare it with the data that it has with something called that loss function, right? It's going to compare it using the loss function, and how off it is or how wrong that prediction is captured quantitatively in something called error or loss. A neural network will then take that error and loss, feed it back into the green section, right, the function part, update itself so that the next time it makes a prediction, that prediction is going to be ever so closer to its data, right? That's what I mean by a machine learning model, or in this case, a neural network, learning from its mistakes. It's able to adjust over time, adjust its predictions so that it gets closer and closer to the data, which it sees as its ground truth, right? So the neural network is really fascinating because it can actually learn from its mistakes. Now, another reason why we're so interested in neural networks is because of this really fascinating fact, and that is that neural networks can come to approximate any natural phenomenon. And that's because of this theorem called the universal approximation theorem. And that comes to say that that tells us that a neural network, given enough parameters, compute, and time, it can come to approximate any continuous math function. And this is really special because any continuous math function, when we think about, okay, what are physics laws? Well, physics laws are just math equations, right? So if a neural network can come to approximate any continuous math function, it can approximate any physics law. And that physics law then captures sort of any natural phenomenon, right? So this is the sort of two big reasons why we're so excited about neural networks. They're able to learn from their mistakes really well, but they also can come to model any natural phenomenon, right? This gives us confidence that the code that we see in our simulations, et cetera, that it actually has like mathematical reliability or predictability, excuse me. So Talked a lot about machine learning and neural networks. Just to sort of sum up the big features here. The machine learning process, the approach, it has these two sort of main features, right? It's built from those brute force simulations. When we talked about learning from its mistakes, right? It needs to constantly compare its results to the data and so forth, run through all these simulations. It's trying to find a brute force solution, right? The second part uses data-driven numerical solutions. So that's the part with the apples. The machine learning model must have a lot of data to be able to learn from those mistakes. And this is very different from a physics-based approach, where you just sort of have an equation and then you're sort of done with it. So we've talked about the Apple example. I always like to sort of ground us in real world examples. So here, an example of a real world for machine learning might be image recognition. So this is something where given some set of pixels, we want to know whether it's a car or a person. So neural networks help us with that, specifically convolutional neural networks. They play a big role in image recognition. Another area where they're quite useful is with stock analysis and the stock exchange. If we want to predict the movement of certain stocks, recurrent neural networks, which are really good at handling time series data, they're used a lot in this sort of realm. So neural networks are just very powerful in solving and modeling a lot of different things in our life. And finally, we can come back to that trade-off question, right? The three guiding principles. So a machine learning approach tends to prioritize things on the left-hand side, right? Machine learning approaches tend to be very complex. So when we come back to this equation here, remember neural networks are just math equations. And for every circle here, that's another variable, right? It's a huge system of tons of variables. So we have this massive, massive math equation. And as a result, this math equation, this model is really quite complex, high complexity. Likewise, the machine learning approach is very specific. Again, when we come back to our apple example here, this model is only trained on pictures of apples. So it doesn't know anything except pictures of apples. We give it a feather, it's not going to know it's not going to have a good prediction, right? So that's what it comes to when a machine learning approach leads to very highly specific models. And lastly, because of that high complexity, high specificity, machine learning approaches also tend to be much more performant because they're able to capture all the tiny things with painstaking detail. They give us much more, they give us much higher performances. And this finally brings us to our big idea, number one, the sort of latter half, that the machine learning approach, it also has drawbacks, right? It has drawbacks in that it prioritizes things on the left-hand side. Well, that means it's not getting anything on the right-hand side. So this is what I mean in the first big idea. Both the physics and the machine learning models, they have drawbacks. So now we want to now we want to ask the question, well, can we do better, right? I don't really want to give up one side or another. Can we do better? And there's been some really clever headway made in terms of hybrid approaches. And as the name suggests here, a hybrid approach is going to use both physics and that machine learning component to be able to approximate phenomenon. And at this point, we can sort of finally talk about our titular character PINNs. PINNs is that hybrid approach, right? So what are PINNs? So PINNs specifically, they stand for physics-informed neural networks, a very sort of dull name. And they're really just neural networks that integrate the physics part, the physics laws, into that machine learning process, right? So that's sort of PINNs. It's a hybrid approach. And that sums up our second big idea of today's talk, which is that PINNs is that combination of the physics and the machine learning. So let's come back to our apple example one final time and think about how a hybrid approach might change how we model this apple. So remember, PINNs is a hybrid approach. So it has the data, right? This is the machine learning. It has the data, but it also has the math part, the math equation, the gravity equation here. So recall that a PINNs model, it makes some sort of prediction. We say, let's say it predicts that the apple goes up. Well, we as humans know that this kind of prediction is quite silly, right? We know that apples don't really fall up, and that's because we have an intuitive understanding of certain elements of physics in our world, right? In this case, for gravity. But the machine learning model doesn't necessarily know this, right? And we don't want the machine learning model to be wasting time making predictions that seem so obviously wrong. So this is where a PINNs model seems to do much better, right? So the PINNs model is going to give this machine learning part, it's going to give it access to that same physical laws that we as humans sort of understand. It's going to give that same access. And when a machine learning model makes a prediction, in this case, the apple falls up, it will not only compare it with the data, but it will also compare it to that physics law, right? So in this case, we compute the acceleration is negative, so we know that the apple should fall down. Well, that's the entirely opposite of this prediction. This machine learning model is able to very quickly correct itself, keep its predictions within the confines of like reality, right? So this is the beauty of PINs. It's going to give two sources, both the data and the physics, two sources that urge or guide the machine learning model to make really accurate predictions. So talked a lot about pins. Just want to sort of summarize those key features. The main feature here is that pins, because they are still a sort of machine learning approach, they're still built from those simulations, but they use the advantage of physics. They're refined by those first principles. Another main feature is that PIN's model can leverage both the analytical and the numerical solution set. So I just want to take a very, very brief detour into the history of pins. So what's really amazing about pins is that pins is a very recent development, right? In 2017 with Razizi is when it was first really formalized. And since then, there's just been a lot of burgeoning research in trying to apply pins to more complicated problems, get them to be more accurate and so forth. So in this case, Lulu's paper on DeepXDE has been a sort of a big titular paper in this regard. But really, that's just it, right? Pins is so recent, and yet it has so much promise. So that's sort of like one of the big things I'll talk about later in this talk is that Pins is a very recent development and has a lot of promise that is not yet fully explored. Um, so at this point, because Pins is so important to this talk, I want to dive into it into a lot more detail. So here is Pins by architecture. So we can just kind of walk through this. We've seen this part before, right? This big NN, this stands for the neural network. So this is sort of a traditional neural network. And the difference with the pins here is highlighted here, the pins loss, this box. In a normal model, it doesn't have this pins box. It's just a normal traditional loss and it passes it downwards. But with the pins model, it has a sort of double loss, right? So we have our output, we have our prediction. We're going to pass it and compare it to the photos of the apples, the data loss. How off is that? So we measure that into a data loss. And then we're also going to compare that prediction with our physics, our gravity equation, right? Capture that in a physics law. Combine them together into a super loss, a combined loss. And this loss, because it has more sources of truth, so to speak, it's going to be a better learner. It's going to be forcing the neural network, this PINS model, to learn much better, a lot faster. So that's PINS by architecture. From another perspective, I want to talk about pins mathematically. So if we can think about this neural network again as a math function, the input layer is just another math function. And we have some input vector in dn dimensional space, right? So this is this input vector. It's just like the data or the metrics of our simulation. We plug it into a bunch of hidden layers. Hidden layers represent all these white parts. There are also math functions of their own. They get passed through, they update with weights, bias, etc. And then out comes the sort of or throughout the input layer, this vector is going to be transformed. And then at the end, it comes to the output layer, which is this last part here. It's going to be updated with the final weights and biases, and then give us the answer, the prediction X, which is now in d-out dimensional space. So that's sort of a high level view from a mathematical perspective. And lastly, just for completion's sake, I want to talk about pins from a coding perspective, since it lives at the intersection of these fields. So here's pseudocode pins via PyTorch. So we first instantiate a model, we find an optimizer, and for every time the pins model is going to train, we're going to take our training data, make a prediction, and then find that loss, the data loss. So squared mean, we're going to use the mean squared error here. This is a normal part, and here with the pins part, we're going to do the same thing, plug in the physics data, get a prediction, find, auto-differentiate, and find the derivatives, and then set our differential equation to 0. And that will serve as our loss for our physics loss. And then again, square mean, mean squared error. We're going to combine both of these losses, loss 1, loss 2, down here, and they're going to have different weights. Typically, they're going to be the same weight. So they're both 1 in this case, but we can adjust them in our models to have different results, right? So we combine the two losses, and then we're going to backpropagate here. So backpropagate is where we pass the combined loss back into the model where the PINS model can learn from its results. So all this to say, this leads us to our third big idea of today's talk, which is that PINS drastically improves upon those drawbacks I talked about earlier. It improves upon the traditional model. And it improves upon those because it is a hybrid approach. It seeks to give us the best of both worlds in this case, high complexity while still being relatively interpretable because of the physics, very specific, but also generalizable, again, because of the physics. And then because of the physics, the underlying physics, it's much more performant. We need much less data, right? So here I'm going to talk sort of the explicit benefits that PINNs gives us. We need much less training data, much less compute cost to be able to run models. PINNs also tend to be much stronger in performance. They have really, really high fidelity to the natural world that we see. And likewise, because PINNs is using sort of an interpretable math formula, we know how to work with math. It opens insight into the black box interpretability questions we might have with AI and neural networks. So these are just like the advantages made very explicitly. So at this point, we can now talk about PINNs and how PINNs sort of relates to our research. So for our research, we had these three main goals. Our first goal was that we wanted to popularize PINNs as a really accessible, useful teaching tool for both machine learning, mathematics, and so forth. And this brings us back to the idea of PINNs being so recent, right? It's only in 2017. A lot of people still don't know about PINNs. The second goal was we wanted to investigate those advantages in PINNs, right? So I talked a lot about those advantages, the hybrid model, et cetera. Well, that's maybe theory, right? Do those advantages actually exist in the modeling applications? Do we see them when we run experiments? And the last goal was to improve upon PINNs just a little bit if we could, because again, PINNs is such a novel technique for modeling. So this part here, just to note, the following examples are from two papers, not one. So they have a little bit of differences in terms of their formatting, but overall, it's still all about PINNs. So the first example we want to talk about where we sort of investigated this is the basic ODE examples. So I just want to highlight the research goals here. Again, we wanted to investigate those advantages. Did those actually exist in modeling? And the examples are all going to be relatively similar. So I'll just kind of do a brief overview of the methodology. What we first did was we found a sort of differential equation we wanted to test it on. We got the analytical solution, we extracted some training data from it, and then we plugged it into a traditional model, right? This is our baseline. And then we're going to plug that same data into a PINNs model, and then we're going to compare. So the goal was to see, well, does PINNs actually do better than the traditional format? And that's sort of what exactly we're trying to do here. So we'll walk through through the examples. This is just sort of a high-level overview of the methodology. So for our first example, we have this basic ODE, right? And this is us picking a differential equation. Based on the initial conditions, we can solve an analytical solution. And then, so for this part here, even though the initial condition is sufficient to give us a particular solution, because we are doing mathematical modeling with like computers, we can't work on an infinite plane. So we do need to set boundaries, additional boundary conditions to be able to constrain the viewing of the graph, right? So even though these boundary conditions are mathematically unnecessary to get a particular solution, we need them for the simulation at least. So that's this part down here. So we have the analytical solution now of this equation. And what we're going to do is we're going to graph it and then extract some training data, right? So here's that solution here in the gray. And getting the analytical solution is useful because the analytical solution serves as a rubric for our models, right? If a model is 100% accurate, it's going to reproduce that gray line exactly, right? So the whole point is we want our models to be able to replicate or to predict, to approximate this gray line. And we want to see, can our models do that? So what we did was we then extracted these few points, these in orange here, the extracted points, and that will serve as the training data for our models. Next, what we did is we plugged this training data into a traditional neural network. And what we see is something really, really interesting, right? The traditional neural network, as expected, does really well when it has training data, but the moment it sort of stops getting access to the training data, it doesn't know what to do, right? Look, the training step is still running and there's no changes to the model because it's completely converged on a solution. It doesn't know what else to do. This is sort of a common recurring theme with traditional neural networks. They're unable to do very well with out of distribution. They're called out of distribution generalizations. Now, we take the same data and we plug it into a PINNs model, and we get something really, really fascinating. So here, the PINNs model not only continues to find convergences or find improvements to the model long after the last training data, but it also is able to find that almost near perfect approximation, right? So in this case, the PINNs model is able to find that, leverage both the physics and the machine learning part to be able to converge on a solution. So here we can compare the results uh, qualitatively, right? So here the PINNs is the green. We see that it almost nearly overlaps the gray, while the traditional neural network kind of loses progress a lot very early on and sort of veers off course, right? We can model the performance of these different architectures, traditional neural network and PINNs, by comparing through the actual error rate, right? So again, error is the quantitative measure of how off the prediction was, how wrong it was. And we see that the PINNs model ultimately reaches a much lower error. The PINNs model, because it has lower error, did much better, right? The PINNs model did much better than the neural network. So at this point, I was thinking, okay, maybe the ODE was a fluke. Maybe the answer is too easy. I would just want to test it again very quickly, right? So I sort of gone through the template of the methodology of the examples. We'll run through this kind of quickly. Find the ODE, get the solution. We graph the solution, get the analytical, the gray, which is the analytical, got some training data, and then we plugged it in again. So we plugged it into the traditional neural network in the PINNs, and we see the same sort of result. Again, the traditional neural network veers off course. It doesn't know what to do the moment it stops getting training data, but the PINNs is able to stay on course and model it exactly. So again, just another view into the error rates. The PINNs model does very well error-wise as well. So far, these two examples have been first order or have been first order differential ODEs. And the idea is maybe we want to test to see if PINNs will do better on more complex equations, right? So here is a class of examples related to harder ODEs. So again, the same thing, picked a harder ODE. In this case, it's a second order. We picked the ODE, solved it analytically, set the boundary conditions, and then we sort of, again, got the training data here. And I wanted to highlight this example here because I talked a little bit about out of distribution before. This case is a really, really strong case of that, right? We only see, in this case, for this solution, we only see the orange points in the sort of the positive half, and the model doesn't know anything about the latter half, right? So in this example, we really wanted to test to see if the PINNs was able to account for these out of distribution generalizations. And I'll show the GIF for this one because it's kind of fun. We plugged it into a traditional model. Again, as we expect, it does very well when it has access to training data, but it completely does not know what to do on the sort of back end, right? It's not able to take advantage of symmetry, not able to take advantage of generalizations, again, outside of the distribution. And the PINNs model is just not as accurate as, sorry, the traditional neural network is just not as accurate. When we did the same thing with the PINNs model, we see something very, very spectacular, and that the PINNs model, like very, very quickly, is able to take advantage of that symmetry and perfectly graph that model, despite having the access the same kind of points, right? So the PINNs model is very good at out of distribution generalizations. And here, qualitatively, we can see the differences between the graphs. And again, from the error rate, we can see the PINN error is much, much lower than the traditional neural network. Just a small note about why this one's so spiky. If we look at the y-axis here, the error rate is very, very tiny. So it's able to jump very quickly because just a small shift can lead to a very big distribution in the results of the error. So that's just why this part's a little spiky. Okay, cool. And now, so far we've talked about very classical examples. We haven't really been talking about physics modeling. So now I want to apply the same kind of principle methodology into physics equations, right? So as mentioned before, as a reminder, harmonic oscillation was a physics law. It measures the bounciness of a spring. And I wanted to see if the PINNs model was able to replicate this, this specific part as well. So following the template, we find the differential equation, we solve it, and then we set some boundary conditions, and then we're going to try to extract some sort of analytical solution. So in this case, the blue is the analytical solution. It's the answer, it's the rubric, the answer key, and we just got a little bit of training data in the case of the orange. We did the same thing, plugged it into a traditional model. Traditional model at first does very well, but it starts to veer off course. Plug it into a PINNs model, and it seems to do very well. even in such nonlinear high complexity equations. Here's a view of the divergence of them, and then again, the error rate. So even with the harmonic oscillation, we see the same result. PINNs does better on higher, more complex equations. And then the last example we want to go over was sort of the highest complexity example we had so far, which is the Berger's equation. And specifically for this one, we wanted to try a different kind of research goal. And that was we were interested in seeing if we can improve upon the PINNs modeling technique. Because again, PINNs is so recent, right? So the changes to this methodology was we wanted to test a specific technique called RAR and see if that helped improve the PINNs technique itself, the PINNs architecture. So that begs the question, okay, what is RAR? So RAR is a residual-based adaptive refinement. And what this does is it dynamically increases its focus on higher error regions. Okay, so this is just fancy talk for saying that the RR technique gets a model to focus more or to pay more attention to or try to model the parts that are harder to approximate, right? So here there's a graph of RR or is a visualization of R&R in action. So for example, up here, this is maybe just a normal traditional neural network. It's going to be looking at all the points with equal attention, right? It's going to focus on all points equally, but maybe we don't want that, right? We don't want that because at the edges of this graph, so this is the Berger's equation, so it's this one. The edges are a lot harder to model, and we don't really want to be treating it with the same kind of weight or urgency as the middle points, which are very easy to model. So the R&R technique helps us zoom in on those harder to model parts, right? So now we have more dots, more attention being spent on trying to model the edges. So as sort of a sneak peek as before, we're going to apply this R&R technique to see if PINNs can be improved to the Berger's equation. Berger's equation, again, it's a physics law that tells us about how fluids might interact in a system. And the first thing we did was, again, we got that analytical solution, right? So this is what the Berger's equation looks like perfectly in terms from a physics standpoint. This is the equation here. This is a 2D cross section of it. And what we did was we plugged this training data in, plugged it into a PINNs, but the PINNs does not have the RR technique. And it produces something like this. It looks pretty close. And then we did the same thing, plugged it in, this time with the RR technique. And it looks pretty similar, right? But it's better seen when we look at the error rates, right? So here in green is the R&R, the presence of that new technique, just the presence of the new technique. And we're trying to see if this new technique of R&R improves the PINN architecture. And in this case, it does, right? In both instances of training and testing. So here in the training, which is the solid line, the PINNs R&R does much better than the PINNs that is just sort of a normal PINNs. And the same thing happens in testing. So here it seems like, indeed, the R&R technique does improve upon the PINNs architecture. So this is just some sort of small advantage that we have in making PINNs just a little bit better. So we've gone over a lot of different examples, wanted to be really exhaustive in terms of finding the truth about PINNs, right? So I just want to summarize. So in all of our examples, what we saw was something really incredible, was that PINNs almost was universally quite better than a traditional neural network on all regards and all different examples, right? The error was always lower. And secondly, for our third research goal, we wanted to see if we can improve upon PINNs. And indeed, we saw that in the Berger's equations as well. Indeed, the error was much lower when it had the R&R technique than when it did not, right? So, and here's just a Google Colab link for anyone who wants access to the code. It's open source, so people can check out the code and play with the models themselves if they want. And with that, can finally sort of come to a conclusion about continuing study. So we've talked a lot about PINNs and how amazing it is, how much promise it has. Well, Professor Kong and I, we want to apply PINNs to potentially solving questions in disease spread modeling or questions in energy consumption modeling. So these are just sort of future directions for our work. And with that, I'd like to come to a conclusion, just to quickly summarize what we've talked about. So the first big idea was we talked about traditional modeling, right? A physics approach and a machine learning approach. They both had drawbacks. And that was the first big idea. The second big idea was that PINNs was a novel approach to this, right? It was that hybrid model that uses both the physics and the machine learning. And it turns out that that hybrid model actually does much better. It does much better than the traditional method. And we built into these three big ideas by talking about modeling, then the different approaches to modeling, talked about PINs, how PINs related to our research, and then talked about continuing study for PINs. And with that, thank you very much. Now open for questions.
All right, thank you so much for the talk. It's very interesting and very informative as well. All right, let's give our speaker a round of applause and we'll take questions. You can either type in the chat or just unmute and ask the question. I have a couple questions. So closer to the end, you talked about the burglars model with the RAR.
Yes.
Right, right, and you had a comparison picture with the one with the error comparison picture with RAR and without RAR.
Right here. Yes.
Right, I'm wondering if there's any reason for that spike there and at that training step.
Yeah. So we actually see this spike on a lot of different results as well. There's like big spikes and so forth. I think that's because the model is first, the PINs model as well as the neural network model is at first, let me go back to, is at first trying to converge on fitting the model really well. And as a result, in that movement to drastically shift its performance, it might land on a spike, right? So then it comes down here, it's fitting the model very well, and then it might hit some sort of nonlinearity or something like that, and then needs to abruptly change to mold itself. That's one idea for why I think there might be a spike.
Okay, thank you. Thank you. We have a question from Avi. Avi says, were there other improvements to PIN other than RAR that you investigated? Why did you select this specific improvement?
Yeah, great question. So far in the research, it was really just the R&R technique. The bulk of our research has been focusing on applying pins to models, right? Sort of do a proof of concept to see if pins really did have those advantages in application. But certainly we're happy to look at future research will be about improving the robustness of pins. We selected R&R because it's sort of a standard improvement technique that was used in other machine learning models. So we just sort of started with there as a baseline.
All right, thank you. And Ryan asked, have you seen any literature on how we can use machine learning to generate our first approximation of the differential equation?
Got you. Yeah, so let me just double check to, have you seen in literature how you can use machine learning to generate our first approximation of the differential equation? So when you talk about first approximation, do you mean like the first time it drew its line? Is that what you mean? Oh, got you. Um, so that's a really good question, and it's a question I get a lot. So kind of what you're very loosely asking is that like why do we want to use pins when we sort of already have the analytical solution? Is that sort of like similar to what you're asking? Okay, so based on my understanding of your question, so pins can be useful in modeling things when we sort of have an analytical solution, but pins are also useful in something called inverse problems, where we don't necessarily have that a priori knowledge of the physics laws. Pins is able to sort of backwards approximate, find the weights and biases, the approximate numerical solution for that underlying physics. So in that sense, it would be able to generate that first approximation of the system, the physics law that we might not have access to. Literature would be Lulu's paper talks a lot about the inverse problem. I should go to the references, so I can show that. Yeah. So DeepXD paper, they do talk about, they investigated where pins is very useful in solving that first approximation of a physics law where we don't have access to. Hope that answers your question.
Maybe I can add to that conversations. I think that's a very interesting questions, and in fact, there are this is essentially the two main direction in the research regarding using data to understand physical systems. either one is that we presume some understanding of the system, and now we try to use, usually that kind of modeling will involve some reductions. And now, one way is to, hey, there are so many parameters to adjust in a particular model, but we have some idea what are the underlying dynamics of the system. So let's use the data to learn those parameters. That's one way. So it's kind of AI data assisting the way we understand what we already have an idea. The other one that Ryan refer to is, hey, let's just let the data drive our understanding. We simply use data to generate the underlying dynamics to the model of the dynamics. So either we start from some idea, so let's write down some differential equation to describe the dynamics, or the other approach is also very natural. Hey, we have so complicated. Let the data drive that discovery process. Let it write down differential equation, and let's start from there and see what we can learn. So it's over the place phrases, and both are very interesting. Lots of people are working in these two direction and the variation of those.
Thank you. Again, Abby has a question. He asks, as a math student, how did you find the journey of being involved in this interdisciplinary study that involves concepts from disciplines like computer science and physics as well? Could you also just approximate how long this entire study took to reach this point?
Got you. Yeah. So coming into UIS as a math student, I was really interested in learning math foundationally because that was something that I didn't do prior. Just like learning math from first principles, right? And I was taking classes and I really wanted to expand upon that. And Dr. Chan introduced me to Dr. Kong. And Dr. Kong was doing research in PINNs, and that's sort of where I suddenly got immersed in this. So by happenstance, I come upon PINNs. I didn't really know what it was at the time I started, but having gotten more involved into it, I've come to really, really like it. So I hope that answers the first part. How long did it take to reach this point? So I'm 3 semesters in, so I guess like sophomore-ish into UIS. But I did have knowledge of computer science, or specifically the engineering part. I had knowledge of the engineering part prior. Um, I would say, yeah, I think so. Dr. Kong is very good at teaching. I will say that. So if you stay with him for as long as I have, you certainly will have gotten farther than I have, I think. So I had a lot of background knowledge I needed to do.
Yeah, I can add some comments instead of question. And first of all, thanks, Chris, to give this presentation. And PINN is not only provide a more efficient way to do computation in many different areas, like in engineering, in biology, but also serve an excellent tool to learn abstract math concept along with a hands-on machine learning coding. To go back to Abby's question, how long is going to be take? It totally depends on yourself, because it looks like we have two ways. If you're good at coding, we can starting from that part. If you're good at math, we can starting from equation. So it total depends on yourself. Okay, and I think yes, the learning curve shouldn't be very steep. Should be a little bit flat. Depends on your background. Yeah, so yeah, that's I hope this answer your question, Arby. And a little bit more heads up information is we in the future in the fifth semester we would like to use PINN to compute a more complex differential equation, such as some certain type of PDE, like the KPP equation, what I have done in my PhD study in 5 years. Whether we can use PINN to simulate this kind of unsolvable, this not solvable, but just learn some behavior of the solutions. That's some our future goal, one of the future goal. And the other goal is we're gonna learn some, maybe use PINN to learn some OD system, right? So like instead of PDE, right? Like the SIR model, whether we can use PIN to to learn some parameter for certain diseases model. Yes, it's something we're gonna learn in the future. And as RB, if you have interest, we can also have a more discussion on this potential area of study.
Oh, I can get back to one of the comment I made earlier, and how machine learning and data is being used to being used to understand the physical nature of stuff. For example, some string theorists string theory is one possible candidate to explain the how the fundamental law of physics works at the fundamental level. But there's a big problem. And one of the many big problems it faces is that which ground state, the lowest energy state of a string theory should corresponding to the reality that we are dealing with. So it is a very complicated problem. And so some string theories is trying to use some machine learning technique to try to guess the string vacuum, the possible ground state of some of these string theory, and hopefully to search for a possible connection to the reality, which I wish them well.
I have a question. Do you know if there's any applications for, there probably is applications for pins on like stock market predictions or option market, because the physics part isn't really restricted to physics, right? It could be other laws that we know, maybe like the Black-Scholes model for like option pricing predicting. Do you know any applications of pins on the stock market?
I don't think there is too many study on that. And again, I believe the PIN is still very new. And he is based on I know some engineer like fluid dynamics. Because the equation, as long as, because PIN is highly related to equations, right? If the equation understand well, PIN gonna behave better. So
Right.
yeah, that's typically, I don't know about the option equation, but yeah, it's more apply in the fluid dynamics so far. Yeah, but yeah, even the SR model is not a very not many more study on that model either. So it's probably because of the high complexity of the disease spreading. This dynamic is it's more complex. But there is for something more concrete like fluid dynamic, as I said, that's gonna be there are a lot of study on that area because that function is understood well, and
Right.
yeah, that's basically on my observation so far, and I'm sure people are starting, everywhere in different field. Yeah.
I see in the comments, Ryan said the thing with physics is when people make the discovery that they publish it, but in finance they don't because they keep the secret and trade it. That's right.
Yeah, it's called physics informed, but in my opinion, it's a mathematical equation informed, right? So yeah, we use physics to represent the mathematical equations. So yeah, could be applied, could be the biological informed, right? Yes, yeah.